Okay, Bismillahirrahmanirrahim. Now, today's topic is based on the periodic table. And
Sir,
yeah,
message please let him in.
who is that?
Abdullah.
You should join. I'm admitting them. Why is he just joining? Those that are joining have been admitted. I'm not delaying anybody. I'm using my system, not my phone. Okay. Now, the periodic table. Can you all see that? Now, where the
Yes,
periodic
sir.
table is just a table that is a table that is having arrangement of elements that requires a systematic arrangement. It's a table that arrange elements systematically based on certain features or certain observations. Okay, and the periodic table is something that scientists have been using even up to the moment for prediction of or for prediction of the behavior of certain elements and observation of future occurrences of those elements. So even when the periodic table was not, the element discovered were not as much as what we have today, scientists have actually worked on designing something similar to this. So which we shall see subsequently as our discussion continues. Now here we have the development of the periodic table. How was the periodic table developed? As you can see here, the periodic table is a vital tool used by chemists to predict the way in which elements react during chemical reactions. It's a method of categorizing elements according to their properties. Scientists started to look forward to a way in which to categorize the known elements about 200 years ago. The periodic table was devised in 1869 by a Russian scientist called Dmitry Mendeleev, who was a professor of chemistry at the St. Petersburg University. Yeah,
Please, can you repeat the name again?
Dmitry Mendeleev. Dmitry Mendeleev is a Russian name. It's not an English name. It's Russian. So Dmitry Mendeleev. So he was a professor at the St. Petersburg University. So, however, other scientists have also made contribution before he started his own. A lot of scientists have worked on how to make arrangements of the periodic table. Some of these scientists include people like Johann Doeriner. He predicted what we call the law of triads. And we have John Newland too, who predicted the law of octave, or we call it the octave rule. These were rules that were predicted. These were rules that were opined by some scientists before Dmitry Mendeleev brought his own suggestion. So they looked at the occurrence or certain features, observable features pertaining to the reoccurring nature of properties in elements. Then they were able to come up with these laws or these rules. So Johann Doerner came up with the law of triads or the triads rule, while John Newland came up with the octave rule or the octave law. So that was that. And again, as you can see, sorry. We have a periodic table here. This periodic table you can see here was the one that was first designed by Dmitry Mendeleev. So his own periodic table was accepted and given preference over others because it followed an acceptable logic and a pattern, and a wide range of elements was incorporated into his own method. So you can see here that this description of the periodic table given by him looks like what we use today. But Mendeleev's classification proved to be the most successful out of all of them, right? Mendeleev arranged all the 63 known elements during his own time. He arranged them in order of their increasing atomic weights, meaning that he used atomic weights to arrange those elements. So, and there were similar, and what he used was, what he discovered certain similarities in same vertical columns. So those elements that have similar properties were classified under the same word, columns. So he called those vertical columns, he called them groups, and he calls the horizontal rows, he called them periods. So whatever element is arranged in vertical was called, in the vertical column, was called group, while those arranged in horizontal rows were called periods. So if necessary, he left gaps in the periodic table. Now, the table that was proposed by Mendeleev had only 63 known elements. Not all the elements were discovered in his time. So those elements that were not discovered, he predicted what would be their behavior, that possibly if so element, a particular type of element is discovered, this will be the possible property. And he was able to do that. And that was why the credit of the modern periodic table is given to him. Mendeleev was able to predict the behavior of some missing elements in the periodic table, just like I have said. So where he left the gap, then he was able to predict what will be the behaviors of those elements. So Mendeleev's periodic table has been modified in the light of work carried out by Rutherford and Moseley. So recently, we get to observe that the periodic table that has been proposed by Mendeleev has been changed in a way. Why? Because while Mendeleev was doing his research, he failed to neglect some other things, because during his time, the atomic number was not discovered. So when the atomic number was discovered, they came to realize that the arrangement that was done by Mendeleev, that means Mendeleev was able to arrange these elements according to their increasing atomic numbers. So he was of the opinion, as the scientists who came after him after discovering the atomic number, we had the opinion that the arrangement made was actually wrong, that I was supposed to do that classification based on the number of protons, which is the atomic number. So the atomic number is actually what is used to obtain or detect or to make a classical arrangement of the modern periodic table. So they now modified the atomic table that was the periodic table that was done by Mendeleev, and they rearranged it, and they made it into a new periodic table. So in the modern periodic table, there are about 218 known elements, and these elements are arranged according to their increasing atomic number or number of protons. So that's hence what we call the modern or the new periodic table. So Mendeleev's periodic table was arranged based on their increasing atomic weights, but the modern periodic table is arranged according to their increasing atomic number or the number of protons. Are you getting it?
Yes, sir.
Okay. Now, to proceed. Now, the modern periodic law. The modern periodic law states that the arrangement of elements in the periodic table is a function of the what? Of the atomic number of the elements. Meaning that what guides the arrangement of elements in the periodic table is nothing else than what? Than the increase, than the what? Atomic number of that element. So it was not dependent on the weight, the atomic weight, but it was automatically dependent on the what? On the atomic number. So that's why when you look at the periodic table, you get to realize that the way the periodic table is arranged in an increasing order of the atomic number. So the periodic table can be used to predict the properties of the element based on its position in the periodic table. So the periodic table organizes the elements in groups and in periods. A period is a horizontal row of elements, while the group is what? The vertical columns of an element. Now, on a large scale, here we have groups. As we have said, that groups are regarded as what? Arrangement of elements in what? In columns, from top to bottom. So in that situation, in the periodic table generally, there are 8 groups of elements in the modern periodic table. 8 groups. So I'm going to look at an example now. So we use that to explain. So the first column is called group 1. The second is called the group 2, and so on and so forth. So some of these groups have special names. For example, group 1. The group 1 element are known as the alkali metals. That's their general name. Then the group 2, we call them the alkali earth metals. They have 2 valence electrons and they are X block. The group 1 have 1 valence electron and they are also S block. We have the group 6. The group 6 are called chalcogenes. They have 6 valence electrons and they are P block. We have the group 7. The group 7 are called halogens. They have 7 valence electrons and they are called the P blocks. We have the group O or group 8. They are referred to as the inert gases, the rare gases, or the noble gases. So the list of them is having a valence of 2 electrons, that's helium, and others have 8 valence electrons, and they are also P block. So between group 2 and group 3 of the period 4 are what we call the transition elements, which are the D block. So let's look at what an illustration of what I'm talking about. Now, looking at this table, can you see that? Can you see the periodic table here?
Yes, sir.
Yes.
Yes, sir.
So looking at the periodic table, I'll beat you. Sorry.
What?
Can you hear me? Can you hear me, please, everyone?
Yes, sir. Yes, sir.
Okay, now here we have the periodic table of the elements, showing how element is being arranged. This is the modern periodic table. So you can see here we have hydrogen. That is 1. So the arrangement of elements here, can you see the cursor? From top down like this. Can you see the way I'm moving it? So this is called the what? The group 1. These are group 1 elements. Okay. In group 1, we have hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. These are the elements you have in group 1. So these group 1 elements are called what? They are called alkali metals. Are we together? So the second one here are referred to as the group 2 elements. Group 2 elements are referred to as what? Alkali earth metals. So the group 2 includes beryllium, magnesium, calcium, strontium, barium, and radium. So here we have the what? The group 2 element. Are we together?
Yes, sir.
Now you can see those ones we have within here. Neglect those ones for now. That is the one that is standing with SC, scandium. Neglect those ones for now. I'll talk about those ones later. Now, leave that to move to these 3. Look at the numbers. The numbers are 1A, 2A. Are you there?
Yes.
Then on top of here, we have 13 there. Can you see where we have 13? This one. We have 3A. Can you see that? So this is group 1, group 2. Here I have group 3A, group 4, group 5. So this is group 3 now. So in group 3, we have boron, aluminum, gallium, indium, thallium, and nihonium. So and this is group 4, carbon, silicon, germanium, and so on and so forth. Nitrogen, group 5. Now the most important ones are group 1, which are known as alkali metals. Group 2, known as alkali earth metals. Then you have group 6, are known as chalcogenes. Group 6 are called chalcogenes. Okay. So you have group 7, known as halogens, right? And then you have group 8 or group O, known as what? rare gases, noble gases, or inert gases. So these are the groups. You have 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. These are the major 8 groups. Now, periods. How many periods do we have? You have 7 periods. What is period? Period is what? The horizontal arrangement in rows. So here we have period 1. In period 1, I have hydrogen and I have what? Helium. Can you see that?
Yes, sir.
In period 2, I have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. That's period 2. Are we there? In period 3, I have sodium, magnesium, aluminum, silicon, phosphorus, blah, blah, blah. Are you there?
Yes, sir.
Yes, sir.
And in period 4, I have potassium and calcium. Now, what is most important here now? Yes, somebody saying something.
I don't understand the period something.
You can't find what?
The period something.
Now, this is the period is vertical arrangement. Can you see the periodic table? Can you see the periodic table?
Yes, sir.
Now, look at the one that, look at where we have 1. Can you see where we have 1? Number 1.
Yes, sir.
Where my cursor is.
Yes.
So, under that region, trace it horizontally to the next one. You see that the other one there is helium.
Yes.
Can you see that? So in period 1, you have hydrogen and helium. Period 2, that's number 2 here. So what do you have under that? Horizontally. You have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Can you see that?
Yes, sir.
So that's for period 2. For period 3, we are going to have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, right?
Yes.
And for period 4, we have potassium, calcium, and blah, blah, blah. Now, you get to realize that for the first 20 elements, 1 to 20, it stops at calcium, right? Now, anything after calcium, that is number 21, you have scandium. You can see that that one is now different. If you look at the position on top of it, on top of calcium, you have 3B. Can you see 3B?
Yes, sir, we can see it.
So those ones that fall between 2, that falls between group 2 and group what? Group 3 under period 4, that is scandium, titanium, those ones here. You can see that there's a gap between them. That one is forming an intermediary between what you've discussed before. So those ones within that sections, we call them transition metals. We call them what?
Transition metal.
So the transition metals there, they are scandium, titanium, vanadium, until you get to what? Until you get to what? Cadmium. Can you see that? Can you see that?
Yes, sir.
Yes, sir.
Yeah, so you call those ones transition metals. Now, transition metals are generally referred to as D-block metals. Now, let me go back quickly to what I've been saying. Now, if you look at the group 1 metals, group 1, when I say group 1, you understand what I mean, right?
Yeah.
Yes, sir.
So group 1 metals, when you write their, why do we call them group 1 in the first place? We call them group 1 because when you write their electronic configuration, the old electronic configuration is going to be the valence electron, that is the last electron, to be 1. For example, if you are to write the electronic configuration of hydrogen, you're going to write just 1, right? If you have to write the electronic configuration of, please excuse me, let me quickly pick a. Now, so as I was saying, if you have to write the electronic configuration of what? Of lithium, lithium is going to be 2, 1, right? Do you agree?
I don't understand.
if you are to write the electronic configuration, you have two methods of writing electronic configuration: SPDF and KLMN electronic configuration. So I'm talking about the KLMN when you have the 8-8 system. So if you are to write the electronic configuration of hydrogen, it's just going to be 1. But lithium has atomic number of 3. So if you are to write, it's going to be 2-1.
Yes.
If you want to write that of sodium will be what? 2-8-1. Right? If you want to write that of potassium, it's going to be what? 2-8-8-1. That's what has been written there. If you look at the table very well, you observe that you can zoom it on your phone. You observe that hydrogen is having 1 down, lithium is having 2-1. Can you see that? Sodium is having 2-8-1. Can you see that? Potassium is having 2-8-8-1. Isn't it?
Yes, sir.
Now, if you look at the valence electron, that's the last electron there. It is 1-1-1-1. So because the last electron is 1-1-1-1-1, so that's why they belong to what? Group 1. So group 1 generally have what? 1 valence electron. Does it make sense?
Yes, sir.
Yes,
now,
sir.
The same thing applies to group 2. When you look at group 2 too, so beryllium here is having what? Atomic number of 4. So to write the electronic configuration is going to be 2, 2, right? So the valence electron, the last electron is having 2 the last shell is having 2 electrons too. So the same thing applies to magnesium. Magnesium atomic number 12 is going to be written as 2-8-2. So you can see that 2 is the valence electron. So calcium is 2-8-8-2. So all of them, they are having 2 as their valence electron. Therefore, they belong to group 2. Do you get it?
Yes, sir.
So if you move also to group 3, that is under boron, aluminium, and so on and so forth, you see that you get to observe also that their valence electron is also what? 3. You see that?
Yes.
And then when you move to, for example, when you move to helium, that's the inert gases. Helium is having 2, right? Now, the simple reason why we did not classify helium in group 2 is because helium is octet. It's duplex. I mean, it is stable already. So it's not going to lose electron or gain electron. So that's why it is better classified under group O. Now, others are having valence electron of 8, like neon, argon, krypton, and so on and so forth. Do you get that? So that is why they are classified as group 8 or group O. Now, going back to what we have been saying again, when you look at this group 1, we can detect their, well, you can detect their block. What block does it belong to? By simply writing their electronic configuration, SPDF electronic configuration. For example, if you want to write the SPDF electronic configuration of hydrogen, what is it going to be? 1s1, isn't it?
Yes.
So now, since the electronic configuration is 1s1, so for this, S is the last electron, that's the last orbital. So it belongs to the S orbital. So that's why it is called S block. So group 1 are generally S block. If you look at all of them, they are all S block. Now, let's take a look at this second one. Right? Lithium. Lithium is going to be 1s2, 2s what? 1, isn't it? 1s2, 2s1, isn't it? Are you getting it? So because it is 1s2, 2s1, we will therefore say that because the last electron or the valence electron belongs to what? S block. Therefore, it's going to be what? I mean, S block element, because the last electron belongs to the what? S orbital. Do you get that?
Yes, sir.
So that same thing, if you vividly recall how to write the electronic configuration of all these elements, you get to realize that they follow the same principle, and all of them here in group 1, they all have S as their valence electron. Okay.
Helium is it in group 1 or 2?
Now I've explained that. I said helium is going to be in group what? Group 8. Why is it in group 8? Now, or group O. The reason why helium is different is because helium is referred to as a duplex structure, because it's having 2 electrons that is already stable. So the 2 electrons will not lose. Helium won't lose the electron, neither gain the electrons. So because it is not losing or gaining, it is stable. So we prefer classifying it under group 8 or group O, because all elements in group O are unreactive elements. They don't react. So it is preferred to classify it under group O than to put it in group 2. Is it clear?
Yes, sir.
So fine. So if you take the same thing with what? Something like magnesium, for example. Magnesium has electronic configuration of 12. If I want to write the electronic configuration, recall vividly, it's going to be 1s2, 2s2, 2p2, 2p6, and 3s2, right? Now, do you still recall how to write the electronic configuration, SPDF?
Yes.
So you can use that logic to detect their blocks, if they belong to block S or block B or block D. So looking at this one, for example, let's say boron, for example. Boron is having an electronic configuration, is atomic number of 5. So the electronic configuration will be 1s2. Okay, who can tell us the electronic configuration of boron? Anybody? Offhand. With atomic number of 5. You can write and then tell me what the answer is. Quickly. Anybody? SPDF electronic configuration of boron. Who is there to say something? Okay, 30 more seconds.
One S2,
Yes,
2S2,
yes.
2P1.
2p1, correct. 1s2, 2s2, 2p1. So what block is that? What block is boron?
Block 1.
No. What is the orbital, the last orbital there?
P.
1.
P orbital. P. Can you see that? So because it is p orbital, so we say what? It belongs to what?
P block.
P block,
P
exactly. P block. Do you get that? So element that belongs to group 3, they are mostly p block elements. If you do the electronic configuration of aluminium, anybody? Can anybody try that of aluminium? SPDF electronic configuration of aluminium. You have 30 seconds. Ten more seconds. Yes, anybody? Who is telling us now? Yeah, go ahead, please. So nobody to give us the electronic configuration of aluminium. SPDF. Yeah, go ahead.
1s2,
Uh-huh.
2s2, 2p6,
Yes.
then 3s2, then 3p1.
Very correct. Very correct. So now 3p1. So what block is that?
That's p block.
P block. Very correct. You're absolutely correct. So that's it. P block element. So aluminum belongs to P block. So all those ones that fall between group 3 downward, group 3, group 4, group 5, group 6, group 7, and group O, they are all P blocks. But those within group what? Group 1 and 2, they are S block. Are you getting it? So now those transition metals starting from 21 down to what is it? Down to this down to 112. Down to 112. They are called what? They are transition metals. That is from 21 to 112 here. Within that capture of the interval between group 2 and they are transition metals. So those ones fall within the d orbitals. Are you getting me? So here we have s orbital group 1 and 2, s orbital group 3 to group O, p orbitals, and then within them you have what? You have the d orbitals. Okay, is it clear? Now quickly, before according to my time here, the Zoom is going to end in 2 minutes time. So let me quickly round off here. So we'll round off our class in the Zoom. Okay. So let me quickly conclude this part. Now we have the lanthanides and the actinides. Let me quickly go back for you to see those we call lanthanides and actinides. Yes. What is happening? Now look at down. Can you see the system, please? Less than 2 minutes. I have lanthanoids. Can you see where we have lanthanoids?
Yes, sir.
And actinoids.
Yes, sir.
So those lanthanoids, those are the ones we call lanthanides. How many are they in number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. They are 15 number. So both actinides and lanthanides are what? They are 13 number. Are we together? So what do we need to know about them? Now first, lanthanides, under lanthanide. Lanthanides are generally F block elements, meaning that their own orbital is under the F block, and they are consisted of 2 series. We have anthanide and the actinides. So under the F block, we have the F block are both anthanides and actinides. They are known as inner transition metals. That's another name for them, inner transition metals. And their series is about 14 up, 14 down. I mean 14, 15. I think it should be 15, 15. That's an error. So the elements in this series have similar chemical properties, lanthanides. So let me quickly stop here because of time, and then we'll complete our class on our Google Classroom. So assalamu alaikum warahmatullahi wabarakatuh.
Wa alaikum salam.
Waalaikumsalam.